Student, you are going to learn the topic electric potential. Electric potential is the next topic from electric potential difference. After learning electric potential difference, it is good to learn electric potential. So first I am writing the equation for electric potential difference. For electric potential difference, delta V equals to VB minus VA, which is equals to WAB upon Q naught. This comes when we have a charge Q and we have this O point, we have a B point and we have a A point. We are moving a test charge from A to B, then this equations come which you have seen in my last video lecture. Now what happened in this situation? A will be moved to infinite. Suppose A is moved to infinite, then the above equation become VB minus V infinite is equals to W infinite to B upon Q naught. You know that V infinite is equals to 0 and VB is equals to V, let you assume W infinite to B is equals to W, let. So you have V minus 0 equals to W upon Q naught. So V equals to W by Q naught. This is the equation for electric potential. So electric potential is defined as work done per unit test charge. Work done per unit test charge in bringing a charge from infinite to a given point in the field of the source charge. In the field of the source charge. It is a scalar quantity and its SI unit is joule per coulomb or volt. This is said to be electric potential. Now you are going to see what will be the expression for electric potential which we are going to use in this chapter. So expression of electric potential. For knowing expression of electric potential, let us have a test charge. Let us have a source charge first. Source charge Q at point O, and let us take point P, point B, point A, and at point A we have a charge Q naught. Since this is a source charge Q, so this apply a force on this Q naught, the force is F, and we are moving this charge Q naught from A to B. Let the distance from O to A is x. So the small distance from A to B is dx. Dx moving in this direction from A to B. And let O to P is R. O to P is R, and moving forward we have infinite. So when the charge is at point A, then force F is equals to K capital Q Q naught upon x square. This is said to be magnitude of force. So work done in bringing charge from A to B is dW small work is equals to F dot dx. Since F is on that direction and dx is in this direction, so both are in opposite direction, so the angle is 180 degree. So you write this is F dx 1 cos 180 degree. F dx cos 180 degree. Cos 180 is minus 1, so you have minus F dx. The value of F is K Q naught upon x square into dx from here. So this is the work done when you move the charge from A to B. But the requirement is to bring the charge from infinite to P point, that is R distance. So we have to integrate it. So integrating both sides with proper limit. Okay, integrating both sides with proper limit. What will be the limit? The limit on LHS side is 0 to W, because work done on infinite is 0 and work done at point P is W. This is on RHS side we have K Q naught x square dx. Integration, we are bringing this charge Q naught from infinite to P point. So we write here infinite and P point the distance is R. So right is R, and we have a negative sign, we know that. So this integration can be written as, this is written as dw integration is w 0 to w. On the RHS side, minus k q q naught taking out, and x to the power minus 2 dx here integrating infinite to r. So here in the LHS side, w minus 0, and on the RHS side you have x to the power minus 1 by minus 1 bigger bracket infinite, right here r. This equation comes because we have the formula integration x to the power n dx is equals to x power n plus 1 upon n plus 1. So if you have x to the power 2 minus 2 integration dx, then the answer will be here at the place of n write minus 2. So x to the power minus 2 plus 1 by minus 2 plus 1, it is equals to x power minus 1 by minus 1. So I am writing this equation according to the help of this integration formula. Now you have this minus and this minus become plus, so you have k q q naught. Here you have 1 by x integration infinite to r. The integration value is w this side work. So k q, this is equals to k q q naught. Put the value 1 by r minus 1 by infinite. This is equals to k q q naught upon r, because 1 by infinite is equals to 0. So the value you find for work is, work w is equals to k q q naught upon r here. This can be written as w by q naught is equals to k q upon r. You know that w by q naught is v, potential. So v is equals to k q upon r, because v is equals to w by work by test charge. So this is the equation or expression for potential which you are going to use further. Here the value of k is 1 by 4 pi epsilon naught. So you can also write v equals to k q upon r, which is equals to 1 by 4 pi epsilon naught q by r. This is the equation for potential. Now let us see the variation of potential with distance and compare with the variation of electric field with distance. So this is variation of potential and electric field with distance r. Let us take V here and R here. Since you know that V is equals to K, V is equals to K Q upon R. This means that V is proportional to 1 by R. So V is inversely proportional to R. So the graph for V is a curve graph in which this distance and this distance are same. So this is the graph for this. Now next, you know that electric field E equals to K Q by R square. This means that electric field E is proportional to 1 by R square. So here this is the distance will be electric is more, and the distance as you come near, as you go below, you have to decrease the distance. So this line indicates about electric field. Here the distance is more, here the distance is less. Now this is the point where these two meet. So this is R is equals to 1, and this is that point here, electric field E and V graph. This is that point where R is equals to 1. If you put R1, then the answer is KQ. If you put R1, then here also the answer is KQ. So numerical value of electric field and numerical value of potential will be same at this point. Numerical value of E and V are same at this point. Let us see a numerical to enhance your concept. Numerical is very important in physics. Here we are taking a charge q. The charge q value is 4 into 10 to the power minus 7 coulomb. Let r distance is 9 centimeter. You have to, this is point O, this is point P. The question is, what is the value of potential here? V potential, part A question number, potential. Now, second part is, if I bring a charge q naught from infinite to this point, and the value of q naught is equals to 2 nanocoulomb, then what will be the work done for that? And it depends on the path or either straight or curve, it will be bring from infinite to point P. So part A is, you have to find the potential at point P. So potential V is equals to K Q upon R. Value of K is 9 into 10 to the power 9, and value of Q is 4 into 10 to the power minus 7. Here it is 9 centimeter, which means 9 into 10 to the power minus 2 meter. So write here 9 into 10 to the power minus 2. 9 will cancel out. So you have, we have 4 into 10 to the power, this is 9 and 7, this is minus, this is plus 2. And when minus 2 will be moved in numerator side, again become plus 2, plus 10 ka power plus 2, 10 ka power plus 2, 10 ka power plus 4. So we have 4 10 to the power 4 volt is the value of potential, part A. Part B, you have to find work done in bringing the charge q naught from infinite to point P. So you know that potential is equals to work upon test charge. So you have work is equals to test charge into potential. Test charge is 2 nanocoulomb. Q naught equals to 2 nanocoulomb. Nano means 2 into 10 to the power minus 9 coulomb. So write here 2 into 10 to the power minus 9 in coulomb, and this is in volt, 4 into 10 to the power 4. So this come out to be 8 into 10 to the power minus 5 joule. So the work done is 8 into 10 to the power minus 5 joule. Now, if the charge is bringing from any path, it does not depend on path because it is path independent. Thus you have learned about potential. Do like my channel, subscribe it and share it. Thank you.